CAP theorem. In my own opinion, I think CAP theorem is a wonderful place to start a conversation around your choice of databases given your requirement, but it will not take you to the ultimate decision. For that, you will need to look at more things. For the practical systems, CAP theorem I think is not enough. Having said that, Eric Brewer proposed this theorem in 2000. It says that a shared data system can have only two of the three properties among consistency, availability, and partition tolerance. When we say consistency in CAP, what we really mean is linearizability consistency, which means if you have multiple servers, in an ideal sense, when you write a data, it should be written to all the server at the same time. Well, the laws of physics wouldn't allow you that. You write on one server and you still have to transport these database changes to the other servers. So you can say that, for your users, they don't feel these differences. It has to be orchestrated in such a way. We will take a diagram to explain this further. So we have this diagram where we are talking about the football match, the final between Germany and Argentina. Let's say Alice and Bob are watching this match, and then we have a referee who declares a goal. This information gets to the leader server. The leader server prepares the transactions and thinks that it can go ahead. It sends the transaction to follower 1 and follower 2. Elias, when he checks the score, he sees that Germany has won. So the insert with Germany's score as 1 and Argentina's score as 0 has reached follower 1 before Elias makes a query from the final scores table, and he shouts saying, Germany won. When Bob, sitting with him in the same room, refreshes his app, he sees the score as 0-0 still. So he's like, what are you talking? The trouble is that insert has not yet reached follower 2 for some reason. Maybe the network is slow, or the database server on follower 2 itself is slow. But this is a case which can happen in MySQL or Postgres default replication configurations. And then this is very normal in asynchronous replications. This is fine in a practical scenario, in a lot of practical scenarios, actually, not all. So your databases, relational databases, which are famous for providing you a good amount of consistency, like your C in ACID, but they are not. So this situation is not consistent according to CAP. So this is not linearizable consistent. Linearizable consistency is actually a far more strict level of consistency, supporting that in your regular transactional databases would make them sort of less performant. Throughput would be less. So that is why they opt for a default where they use serializable consistency and not linearizable. In the default way, you can change configurations and then try to get there. Availability in CAP means that every request received by a non-failing database server in the system must result in a non-error response. Note that it is not sufficient that some of these or one of these or everyone else but one of these return a non-error response. And then we have partition tolerance. So given the distributed nature of databases that we are talking about today, we don't really have a choice in this matter because the network lines will be cut. That's not in our control. Given the sort of cloud operating model, it's actually not even sort of in our control in any way. We can't see it, we can't touch it. So partition tolerance will always be there. So you actually have only two choices. Either you go for consistency or availability as per CAP. So this is the diagram that depicts the CAP system scenario. You have data center 1, data center 2, and then there is a network interruption between the database servers in both the data centers. So while the network is down, that's when you think of the CAP theorem. You have two choices. You either allow your users to connect to data center 1. So in our example, Alice might be connected to data center 1. And when Alice connects, knowing that data center 1 cannot talk to data center 2, you can either return the result, in which case consistency is violated, because if Bob is connected to data center 2, Bob gets a different output and Alice gets a different output. And if you sort of say that, if my data center 2 is probably not reachable, so I'll shut it down, you make all my users move to data center 1. In that case, you still have data center 2, which is available, but it's shut down, so it's not returning responses right now, although it was not failing. So you compromised on availability because it's still up and it doesn't return a response.